Okay, so okay, good afternoon, everyone. Hope all of you had a good lunch. Well, we come to the final tutorial of this year's winter school. It's my privilege to introduce our speaker, Professor Guy Katz. He's an assistant professor at the Hebrew University of Jerusalem, Israel. He received his PhD at the Weizmann Institute of Science in 2015. His research interests lie at the intersection of formal methods and software engineering, and in particular, in the application of formal methods to software systems with components generated via machine learning. Over past few years, Professor Katz has been the leader in applying SAT+SMT techniques to very exciting area of deep verification of neural networks. So it's a great privilege for all of us to be able to hear from one of the leaders at an exciting application of SAT+SMT solvers. And I'm very looking forward to the rest of the day today. So over to you, Professor Katz.
Okay, thank you very much for the introduction and of course for the invitation. I'm very happy to have this opportunity to talk to you. And as Kuldeep and I were talking before, it's unfortunate that we can't do this in person, but maybe sometime in the future. So I'll start very shortly. I wanted to say that I will try to stop very frequently to give you an opportunity to ask questions. If you prefer to write in the chat, you can go ahead. I will also try to address these questions and comments that you write, and hopefully we can make this work. Okay, so let's get started. So a tiny bit of background, which I'm sure most of you are familiar with. So nowadays, we really have software systems everywhere, right? Software is controlling our lives, phones, airplanes, hospitals, and the complexity of this software is increasing, right? We want to write software, we want to create software systems that do increasingly complex things. And one, catchphrase that is very hot right now is autonomous driving, right? If you think about an autonomous driving system, then you really need a very complex piece of software in order to manage it. And as I think every student who took a software engineering course knows, manually creating software is very difficult. You think you get it right, and then you start debugging and debugging and debugging, and it's a very difficult undertaking to get your software correct, especially if you want it to do something very complex. So now in computer science, we're seeing this trend, right, which has really taken over the world of computer science. At least at the Hebrew University, if you attend the colloquiums, you'll see that every second talk at least is about machine learning. Right, so what people are doing is they have a set of requirements, right? So think autonomous driving, a very complex system that they want to create. And they don't know how to do this manually. So instead, they extract pairs, examples of how the system should behave. Right? So you get these pairs and you give them to a machine learning algorithm. And then the machine learning algorithm, which is what the machine learning folks develop, these algorithms give you back an artifact, a black box, right? Which you can think about as a piece of software that somebody wrote for you, right? You didn't write it yourself. The machine wrote it for you. And this artifact satisfies the original requirements in general, right? It usually does a very good job. And this kind of programming using machine learning has really taken over entire fields, right? If you think about image recognition, this is a field in which today the state of the art is simply machine learning, right? There are no more handcrafted algorithms. It's really machine learning that has taken over. Game playing, autonomous driving, all of these systems are now, all of these fields are now done using machine learning. I should probably add protein folding, right? This is from a very recent piece of news that machine learning has overcome yet another major challenge in computational biology. So really machine learning is taking over the world. And now the question is, okay, so we have this amazing piece of technology, but what happens when things start to go wrong? So here I usually have this short video. I will try to show it to you. I hope it will be okay over Zoom. So yeah, it's a little jumpy perhaps, but what you see here is a Tesla Model S. It's driving in autopilot mode. So the footage is from a car that's driving behind the Tesla. And now pay attention to the left side of the road. Okay, so I hope you were able to see that the Tesla was driving happily on the left lane, and suddenly there was some road construction going on, and this yellow fence. Right, I can try to pause it on that second. Right, so so the Tesla bumped into this yellow fence, and of course this was a pretty mild accident. Right, so nobody was killed or injured, and the Tesla actually was able to continue driving. But I think this really conveys the point. Right? If you want to use machine learning to control autonomous vehicles and you're going to sit in these autonomous vehicles, then you really want to be sure that these kind of accidents do not happen. Right? So this one was pretty mild, but there have already been fatal accidents involving Teslas. Right? So this is a real concern. Right? So we really want to get our autonomous vehicles, make sure that they are correct. Right? Make sure that these systems are correct before we deploy them in our autonomous vehicles. So really, the thing about black box artifacts is these neural networks is that they're super useful, right? The technology is accessible to non-experts. That's great. But these systems are opaque, right? We didn't write them. We don't know how they are working internally. We only know that they sort of satisfy the requirements. And all of the things that we traditionally do for quality assurance simply do not apply when you talk about machine learning. Right? So for example, code reviews, refactoring, writing invariants and specifications, all of these things that we do for traditional code that we are taught that are good practices to have, to follow, it's really unclear how to do them for machine learning artifacts. Right? You get back this black box artifact, and how do you do a code review? How do you refactor it? How do you write a specification and invariants? It's really unclear. So this is really something that we have to address if we want to use this technology for safety critical systems. So I already gave you one example with the autonomous vehicle, right? The Tesla example. Now let me give you yet another motivating example. And this system is a system called ACAS Xu. So ACAS stands for Airborne Collision Avoidance System. And XU means it's for unmanned aircraft, for drones. And this system is actually a standard that's currently being developed by the American FAA, the Federal Aviation Administration, which is the organization in the US that is the regulator of air traffic. Right? So they're a very important organization when it comes to world air traffic, really. And the FAA came to the realization that we have an increasing number of drones flying around in the sky. Right? If you may have heard that companies like Amazon want now to even start doing deliveries using drones. Right? So the number of drones is really increasing, and it's expected to continue to increase. And there is a problem, right? If you have many drones flying around, then they can bump into each other. And drones can be destroyed. They can fall on pedestrians that are walking below. Right? This is not good. We don't want any collisions between drones. So the FAA is now creating this new standard called ACAS Xu, which is going to be a system, and it's going to be a standard and a system. And the system is going to be mandatory for drones in the US in the future. And the system is going to be airborne, right? So it's going to sit on top of the drone. This is our drone. They call it the own ship. That's us. And the system is going to read sensor information, right? So there is some other drone nearby. They call it the intruder. It doesn't have to be malicious. And they just call it an intruder. And the system reads some sensor information. So things like our speed and the speed of the intruder, some angles and distances. So physical readings from the physical world that indicate the situation between the own ship and the intruder. And then the system needs to make an advisory. Okay, so an advisory is a recommendation that the system makes to the operator of the drone, or if it's a closed loop system, then you can think about this is the controller, right? So this is what tells the system what to do. And the 5 advisories that the system can make are either clear of conflict. This means you can fly straight, there is no danger of collision, or strong left, weak left, right? So this means you need to turn left, and it tells you by how many degrees. And strong right, weak right means that you need to escape to the right. And the goal is simply to avoid a collision with the intruder. So I think the declaration of the statement of the problem here is pretty straightforward, right? We all intuitively understand that if the other plane is coming at us from the left, then we want to escape to the right. So this is the system that the FAA are trying to build. I will stop for a second for questions. Usually this slide raises some questions. So now is your opportunity.
So this specification that there should not be a collision, this is kind of informal, right? And how does one?
Right. So I will get to the specifications in a second. But yeah. So the FAA knows how to formally define some of the specifications that they want.
Okay.
Anyone else? No. Okay. So what the FAA did first was they said, okay, we have this problem that we want to solve. Let's try to write a piece of software that will solve it. And this is what they did first. Right? So they tried to manually solve the problem using their experts sat down and they tried to write code that will do this. And so this turned out to be unsuccessful. And the reason is that they have this set of accuracy tests. So after they create the system, they run tests to see how accurate it was, and they couldn't get the accuracy level high enough. So the intuition here is that when the situation is very simple, right? If you know that the other drone is very far away, then it's easy to say clear of conflict. But in all the corner cases, right, where the two drones are closer together and the velocities are high, then figuring out what to do is complex. The physics is complex. So they couldn't get the success rate high enough. I think their success rate was about 95% among the test cases that they have. And when this failed, they tried something else. They said, okay, instead of writing software that will do this, let's create a very large lookup table. So these tables were created using Markov decision processes. It's not very important, but in the end, what they got was this huge table. And the idea is that you go, right, you read the sensor information, and the sensor information gives you a row in the table that you go to. And in this row, in this cell, it says, well, if this is the case, then turn right. So they created a very large lookup table that does this. And if your sensor reading does not match a particular cell in the tableau, then you interpolate, right? You pick the nearest neighbors and you do some average and you decide what to do. So this was better, right? The precision level went up, but this had a problem that the tables were very, very large. So remember, they're going to put these things on drones, and on drones, you have limited battery, you have limited memory, so they don't want to put a huge lookup table. And then what they did was they switched to neural networks. So the motivation originally was compression. They said the lookup table is too large, the neural networks will be much smaller. And indeed, this gave them a very nice reduction from 2 gigabytes to 3 megabytes. Okay, so very nice. But as it turns out, the neural networks that they trained for compression actually outdid the lookup tables even when it came to precision. So the intuition is that neural networks give you a better interpolation because they're smooth. Right? Unlike a lookup table where you have cells that are discrete, a neural network is continuous, so it is better at the interpolation. So this is the story of how the FAA came to use neural networks, or to consider at least using neural networks for the ACAS Xu system. And of course, we have here a very interesting situation, right? Because this is a critical system. You don't want any collisions at all. This is a very respectable organization, right? It's the FAA. They want to be sure that the system is correct before they release it. But they don't know how to certify these systems. Okay, so they have a lot of experience certifying traditional software. They know what to do before they install a new system on a new kind of aircraft. But now they're going to use neural networks and they have no idea how to start. Right? What do you do with neural networks? How do you check that they are correct before you install them? So this, I think, is a very nice motivating example for the need to certify and to verify neural networks. I'll stop again for questions before I continue.
So, Guy, I guess when you say switch to neural networks for compression, so there was a particular depth of the network, there was a particular size of the network they had in mind, or they just...
Yeah, so they have particular networks in mind. I will go to the dimensions in a few slides, but the networks are not very large. So they have 8 layers each and a total of 310 neurons, which is considered quite small in the neural network world, but it was enough for what they needed.
Right, okay.
Okay. So what can you do, right? So you have a neural network, you have this black box artifact, and you want to be sure that it is correct. Okay, so what can you do? So the FAA started with encounter plots. So this is an encounter plot. So what they do is they take one of the neural networks that they trained, and they say, okay, well, let's run some simulations. Let's start feeding input cases into the network and see what the network says. So what you see here is a plot that they get as a result of this process. So here in the center of the picture is the on-chip. That's us. This is the intruder. And the plot shows you what the neural network says based on the location of the intruder. So for example, if the intruder is here, so it's very far away, or if it's here, if it has already passed us and it's flying away from us, then we are in the white region, which indicates clear of conflict. So the network says, don't do anything. You can continue flying straight. If the intruder is in this region, weak right, it's coming at us from the left. So the network tells us to turn right. And likewise, strong right, strong left, and weak left. So I think intuitively this is pretty clear. And they get these plots by running a finite number of points through the network. Right? You pick a very large number of points, but it is a finite number, and you run them through the network, and you draw this little plot. But the question is, how can you be sure that there are no problems that you didn't check? Right? So this is usually the case where you talk about testing versus verification. You think that this entire region is consistent, but you don't know. Maybe there is a point here that you just didn't test. And if you had tested it, then you would have seen that for that particular point, the advisory is incorrect. So this gives you some sense that the network is doing what it should, but again, this doesn't give you any guarantee, and this is a critical system.
So this encounter plot is independently generated by the testing team, or is it? I mean,
So,
is it desirable behavior, or is this the actual?
So what they do is they generate these plots, and then they have the experts look at them and say that this is what they want.
I mean, for example, I see that the regions SR and SL are not completely symmetric, neither are WR and WL. So
right, so we don't expect complete symmetry typically in neural networks because there is a lot of randomness introduced when you train them. And also, this really depends on the kinds of parameters that you fix. Right? So these plots, remember that this is the input has many dimensions. Right? So you have distances, speeds, angles, and for these encounter plots, they typically fix most of these inputs, and then they let just a few of them change. Right? So the shapes that you see also depends on the speeds and the angles that were picked for this particular encounter plot.
okay, so this is the projection of a much higher dimensional space onto.
Right, exactly.
And these are, to come back to my question, these are generated independently and then tested against the neural network, whether it's following this.
No. So this is what the neural network does. Right? So you generate these by executing the neural network, by evaluating it. Then you draw this picture, and then a human expert looks at it and says, this is okay, or this is not okay.
Oh, I see. Okay.
Any other questions? Okay. So of course, this naturally brings me to verification, right? Which is what we are here to talk about. So in verification, which I imagine you have talked quite a bit, probably already during the summer school, you are given a program and a property, and you ask whether the program always satisfies the property. And you either show that this is indeed the case, or you provide a counterexample. Right? So you give back a concrete example for which the program does not satisfy the specification property that you have. And this, of course, gives you a much stronger guarantee than testing, because this can prove that a bug does not exist. Right? Testing can only find bugs, but verification can prove that bugs do not exist. And of course, the reason that people use testing and not verification in general is that testing is easy and cheap, and verification is complex and expensive. So in the world of verification that has existed for several decades, right, probably 6 decades or so, even more, there's been a lot of traditional work on traditional systems. So we know, or sort of know, how to verify code that people write, and we can handle in various ways and techniques common structures that we have, right? So things like loops, conditions, we know how to work with these things in traditional verification. And we also have some ideas of what are the properties that we need to check. Right, so if I give you a C++ program, you might say that, well, you want to check that there are no array overflows, that nobody divides by 0, that nobody dereferences a null pointer. Right, we have some ideas of what it is a good idea to check. And there has been a lot of work on scalability and various tools and techniques. We know how to tackle this problem. And now suddenly we introduce this new kind of software, these neural networks or these other pieces of software that machine learning generates for us. And now the question is, how do you do all of these things for this new kinds of software? And this is, this is a very interesting question. And you could ask, well, is this even worth the effort? And I answer that yes, right? In my opinion, at least, this is definitely worth the effort. especially if you have a safety critical system. And this is usually the case in verification. You have to invest in order to get it to work, but if your system is sufficiently critical, if you have enough to lose, then this is probably worth it. So one other motivating example before we continue. So we already saw the Tesla example and the ACAS Xu example. Here is another example that if you've never seen before will probably shock you a little bit. All right, so in 2014, a group of researchers observed that there was an interesting phenomenon in some neural networks. And what they did was they took an image recognition network. So one of the tasks that neural networks really do well, image recognition, much better than handcrafted software. And they took one of the networks, neural networks that was state-of-the-art at the time, and they gave it this picture here. So it's an image of a panda. And the neural network replied correctly that this is a panda, and it also gives itself a score, right? It says this is a panda, and I'm 57% confident that this is so. So this was, of course, the correct answer, as you expect. And then the researchers added this noise, right? So the noise, the idea is that you have here, for each pixel, you have a tiny bit amount of noise, a tiny amount of noise. This is what this epsilon does. It really reduces the noise to a very small perturbation. And then you overlay, you take these pixels and you put them on top of the panda here. And what you get is this image on the right. Now to the human eye, this is completely identical to the original. Right? You can stare at it for a while and you will not be able to see any difference. Only now the neural network says, well, this is a gibbon, a completely different animal. And not only does it make the mistake, it also does it with 99% confidence. Right? So it declares with the absolute confidence that this is a gibbon. And when this was discovered, this was very troubling because up to that point, people thought that neural networks sort of mimicked the way that a human processed this image. But you see, a human still says that this is a panda. Only the neural network now makes a terrible mistake. So they observed, so this was not just limited to this particular neural network. They observed that in a whole family, a variety of neural networks, small perturbations of the inputs will lead to misclassifications. And since then, so they were already able to find these examples, but since then, this has been a very active field of research. And we now know that these adversarial examples, these perturbations, are very easy to find. Right? If an attacker has your neural network, it will be very easy for them to find these perturbations. So you might say, okay, big deal, pandas, gibbons, you know, who cares? So here is another example, right? So this time it's a neural network that does image recognition as part of an autonomous driving system. So it's intended to identify traffic lights. So you start with an image of a traffic light, you change 11 pixels, and suddenly the neural network says that this is a kitchen oven. So again, if we go back to the autonomous driving example, if you're going to sit inside a car that is running this neural network, you probably don't want to have this phenomenon happen. And this doesn't even need to be some malicious adversary, right? This can be reflection from the sun or a scratch on your camera or weather conditions, right? Snow or ice or whatever. Many things can change pixels in the image that you see. And if this phenomenon exists and you install this system, you know, on millions of vehicles, then statistically this will happen. And you really want to make sure that your system is robust to this kind of issue. I'll stop again for questions. You can also write in the chat if you prefer. Okay. So it turns out that this is not even a random thing, right? So you can even have what they call the targeted version of adversarial inputs, where an adversary picks the kind of misclassification that they want. And people have carried out these attacks in the real world, right? So they can print out images for you and post them, and an image recognition network that is connected to a camera will make a mistake. And this is not just image recognition. It's been done for audio analysis and all kinds of neural networks. And there are many dangers here, right? So natural malformation of input or some adversary that is out to get you. And this is really a very serious security issue, right? So if previously we talked about safety, now this is also a security problem. And people really want to be sure that their neural networks are not susceptible to this kind of problem. So you can define something called adversarial robustness. Okay, so if you have adversarial attacks or adversarial inputs, adversarial robustness is a measure of how resilient your network is to this kind of attack. And what you do is you can apply various techniques that people have developed to improve the robustness of your neural network. And still, even though you can do this, there is a problem here that you're defending only against the attacks that you know. So typically what happens is that you have this arms race. Right? Somebody develops a new attack, a way to find adversarial examples. And then somebody develops a defense. Right? So a way to train the neural networks in a way that makes them less susceptible to this particular attack. But then the next day, somebody comes with a fresh attack and it breaks all the existing defenses. So this is a problem. And it turns out that verification can be the silver bullet that will end this race, right? Because you can use verification to prove that your neural network is robust. And once you do this, you know that your neural network is robust even against an attack that has not been developed yet, even against an attack that will only come along tomorrow. So this is another interesting application for verification also when it comes to security. Okay? So not just safety, but also security. Okay, so this was the introduction. So let's see the roadmap for the remainder of the talk. So we know that machine learning software is becoming widespread. We have seen that there are many problems with them. So I showed you a few problems, but really machine learning needs to be verified. It needs to be certified because there are all kinds of issues with it. And this is a very new and significant challenge because machine learning techniques have really taken over the world very recently. So people have not yet caught up. Right? You still need to develop these verification techniques. And up next, I will focus on neural networks. We will talk about the verification problem there, and we will see why neural network verification is hard. I will quickly survey some of the state-of-the-art techniques that people are using, and then the bulk of my talk will be devoted to the SMT angle. So I will describe to you one approach for verifying neural networks that is SMT-based. It's called ReLUplex, a project in which I was involved, and we will discuss it in greater detail. Okay, so this brings me to the second part where we will define what neural networks are. I'm not sure if you had talks about neural networks already or not, but in any case, let's make sure that we are all on the same page. So if you have never seen one, this is a neural network, so say hi. So this is just a graph, right? It's an ordered, it's a weighted graph, a weighted directed graph that is ordered into layers. And each of these nodes is called a neuron, either a node or a neuron. And these neurons are organized into layers, as you see here. So the inputs come in at the first layer. You do some mathematical computation that gives you values for each of the other neurons, layer by layer. So each time you compute another layer until you get the scores of the output neurons. And this is the output that you give to the user. And the typical sizes of these things can be from hundreds to millions of neurons, right? So you can have really huge number of neurons for state-of-the-art neural networks. So these are huge artifacts. They have many, many nodes. So the first layer is what we call the input layer, right? So in the ACAS Xu example, if you think about the drone collision avoidance system, then your input layer you will assign the values according to your sensor readings. Okay, so you feed the information that you have into the input neurons. Then you do the mathematical computation layer by layer until you get values for the output layer. And the output layer in the ACAS Xu example can be the scores for the possible advisories. So one neuron represents turn right, another neuron represents turn left. And all of the layers in between, so the layers that are not the input or the output layer, are called the hidden layers. And additionally, each edge in your neural network has a weight assigned to it. And these weights are what defines the behavior of the neural networks. So let's talk about how you actually evaluate these things, right? So first, you have already your input values. So they are given by the sensor readings, for example, in our ACAS Xu example. And then each layer is computed from its predecessor using the weights. So the weights are part of the neural network. They are predetermined. They are given to you. And also activation functions. So let's see an example, right? So suppose you have 3 neurons here in your previous layer. So this can be the input layer, or this can be some intermediate neuron that you're trying to compute. So you already have values for these. And you know the weights, right? So each edge has a weight. This is given to you with the neural network. And you now want to compute the value for the following neuron, for V4. So the way that you do this is first you compute a weighted sum of the previous values that you have, and then you add some activation function. So f here is called the activation function, and the output that f gives you is the result that you assign to V4. So what kind of activation functions do we have? So the most famous or common one today is called ReLU, rectified linear unit. So this function is defined like this. So f of x, the ReLU of x, is the max between x and 0. So if this function, if you give it a positive input or a non-negative input, this is what we call the active phase. And then this is just the identity function. Okay, so you get back the x that you gave it. So for example, if you assign 0, 2, and 3 to these nodes and you do the weighted sum, you get 1, and then the ReLU of 1 is 1. This is what we call the active phase. On the other hand, if you have a weighted sum that turns out to be negative, this is what we call the inactive phase. In this case, the function just gives you back 0. Right, so here the weighted sum is -2 and you get back a 0. So this is what we call the inactive phase of the ReLU. So this is one activation function. There are others, but this is, I think, today one of the most common ones, ReLU. So there are some other layers that you can run into. I will briefly mention them. So we have pooling layers, so layers that compute maximal value of the inputs that you give them, or average pooling that do an average of other neurons, or you have sigmoid neurons, which compute this function, and a bunch of others that I won't go into. So really many activation functions, but we will talk mostly about ReLUs that are very common and successful today. So any questions about the definitions of a neural network? You're all very, very quiet. Okay.
The slides are very good, so they are explaining.
Well, okay. Well, flattery will get you a very long way. Okay, so good. So let's now talk about neural network verification. Okay, so we have these neural networks, and we said that we want to verify them. So what does it mean to verify one of these creatures? So this is how we define the neural network verification problem. So given a neural network N that maps a set of inputs X into a set of outputs Y, so these are vectors, right? So you can have multiple inputs and multiple outputs. You have some input property, and so this is sometimes called the precondition. You have a property P that tells you what kind of inputs you care about, and you have a property Q that tells you what kind of outputs you care about. The question is, does there exist an input, a concrete input X0 that is mapped to output Y0 such that X0 satisfies P, it satisfies the precondition, and Y0 satisfies Q, the postcondition. Okay, so this is the verification problem. And the idea is that P characterizes the inputs that we care about. So for example, if I'm talking about the ACAS Xu example, P might say, I only care about situations where the intruder is very far away. So this will be P. And Q will typically characterize the undesired behavior that we are looking for. Right? So if we want to say, when the intruder is far away, the network never tells me to turn left, then Q will be, the network tells me to turn left. And then the question is, does there exist an input X for which the intruder is very far away, for which the network tells me to turn left? So I'm looking for the mistake. So if we get the negative answer, if we get unsat, then we know that the property that we really want to hold holds. And if we get sat, then this is our concrete counterexample. We get back an assignment. We get back X0 that introduces an error, right, when you feed it through the neural network. So this is pretty standard in verification, but remember, you always negate the output property that you care about.
So I have one quick question. So in the neural network model that you showed, it's all feed forward. So
Right.
is there a specific reason? Because there are these other network models also which have feedback loops and recurrence and all of that. So is there a specific reason that you chose that model, or?
So that's a great question. So there are, as you say, there are networks that have sort of feedback loops. They're usually called recurrent neural networks, or well, there are some other terms, but usually recurrent neural networks. And these networks are typically used when you have some context involved, right? So for example, if you do natural language processing, then you want your neural network to remember some of the history. And this is when you need these feedback loops. And the networks that we're seeing that we will talk about today are feed-forward, and they are very widespread, right? So they're used typically for things like image recognition, where each input is independent of the history. And this is where the verification folks started, right? So this is the question that we solved first, or started solving first. And there have already been some works that have showed how you can take the feedback loop case, the recurrent neural networks, and reduce the verification problem into a verification problem over feed-forward neural networks. But then you typically have a step where you need to introduce some kind of invariance of the recurrency, the recurrent nature of the neural networks. So this is similar to verifying programs with loops. And this is a very interesting question, which unfortunately I won't have time to talk about today.
Okay, thanks. Yeah, maybe in the breakout sessions we can have a discussion.
Sure, sure. Any other questions? No. Okay. So, okay, so this is the example that that I gave you verbally, right? So if you want that when the intruder is distant, right, you want to verify something that involves only inputs when the intruder is distant. So if your first, right, so if your input vector has one coordinate, the first coordinate that indicates distance, so you specify your P to say that this distance needs to be greater than some value. And your output property Q, well, you will say that you can say, for example, that you want the advisory to be anything other than clear of conflict. So if output number 0 indicates the clear of conflict and the other outputs indicate other advisories, then you say either output number 1 is greater than the output number 0, or output number 2 is greater than output number 0, etc. And so this will tell you that at least one of the other outputs is greater than clear of conflict, and consequently, clear of conflict is not the advisory that wins. And so this is the opposite of what you really want. So if you get unsat, this means that your system is correct. And if you get sat, then this is a counterexample that you can show to the FAA folks and justify the project that you have carried out. So you can also do the same for adversarial robustness. It's really the same thing, right? So for example, if you want to ensure that given some point x0 and a given amount of noise delta that the adversary can use, the classification remains the same, then you can formulate your property P to say that you're only looking at inputs that are very close to your x0. Right? So if x0 is your panda, then you're only looking at inputs that are the panda plus some small perturbation, less than delta. And right, so this you can formulate on each of the individual coordinates of the input. And your output property will be that the classification is incorrect. So you would say that at least one of the other outputs got a higher score than the output that represents a panda in this case. So again, you can reduce this into the same kind of problem. And again, unsat means that your system behaves as you expect. And it really turns out that practically every interesting problem that we know today can be reduced into this simple setting. Okay, so a neural network, a precondition, and a postcondition. So here is the first unfortunate result. Okay, so it turns out that for a neural network that only has ReLU activation functions, and if you specify your properties P and Q as conjunctions of linear constraints, then the verification problem is already NP complete. Okay, so you see there are some restrictions here, but these are really, the restrictions are to the most simple case, the most simple variant of a neural network that you might want to verify. So you take a neural network that has only one kind of activation function, only the ReLUs, which are the simplest function really out there today. And you limit your properties to only have linear constraints and to only have conjunctions. And still, even with these restrictions, the problem is already NP complete. And it's NP complete in the size of the neural network, right? So if the neural network, if you add one neuron, then you double the complexity of verifying the neural network. If you have 300 neurons, then you need to do 2 to the power 300 operations in the worst case in order to verify it. So what is the intuition? Why is this problem NP complete? This is worth looking into because this gives you some intuition into the verification problem. So proving that the problem is NP is pretty simple, right? If you are able to find a witness, if you are able to find a counterexample, then you just feed it through the neural network, you evaluate it, you can do this in polynomial time, and this is easy. You check that the input satisfies P and the output satisfies Q. But why is the problem NP hard? Right, so this we can show using a reduction from free SAT. And I will briefly go over the reduction because it gives you some understanding of why the problem is difficult. Or maybe before I show you the reduction, any questions about the statement of the verification problem?
So the inputs are what fixed bit width, fixed length representations. Because if I have a real number, then I mean the operations themselves could be very complex, right?
Right. Yeah. So for let's assume that everything is represented as a floating point number.
So for a given precision, I mean,
right.
fixed
Yeah.
number of bits. Okay.
Yeah.
So I have a quick question regarding delta. So this delta is expert knowledge here. I mean, how does one?
So that's a very good question. Also, I will have some slides on that. So generally, yes, generally it's expert knowledge, but there are some automatic techniques for figuring out this delta.
Okay.
But here we're just defining the problem, right? So you assume that somebody gives you the query and you need to solve it.
Yeah.
Okay. So let's have a look at the reduction. Okay, so in 3SAT, right, you have a bunch of Boolean variables. You have I'm sure you had a session about SAT solving, so hopefully you remember this stuff. So so you have your input formula is a conjunction of clauses, and each clause has 3 literals in it, right? So a literal is either a variable or its negation. So you have clauses that look like this. And the goal is to find a variable assignment that satisfies the formula or declare that there is no such satisfying assignment. So in our reduction, we will take a formula and we want to translate it into a neural network such that if we're able to verify the neural network, then we are able to solve the satisfiability problem. So how do we do this? So first, if you look at a clause, right, so when you start with a clause, you have inside either variables or their negations. So what we're going to do is we're going to assume, for the sake of simplicity, that every variable, input variable, is either 0 or 1. And now we want to express literals. Right? So a literal is either a variable or its negation. So if we have a variable without negation, then we just use it. It's part of our input. If we have a negation, then we can simply compute it using a weighted sum. Right? So if we want the negation of xj, then we just do 1 minus xj, like this. So this gives us the negation if we need it. Right, so you can see that that Q computes the negation of the input in this case. So negations are very easy. But what do you do with disjunctions? Right, so remember, once you have a clause, you need inside each clause you have a disjunction between 3 literals. So I claim that the following construct, this neural network construct, computes a disjunction. So what you have here, you have the 3 literals, which are each 0 or 1. And you are going to feed each of them into this TI as a weighted sum, right? Each with a weight minus 1. And you're going to add the constant 1. Then here you have the ReLU, right? So remember, in each hidden node in your neural network, you have the ReLU function or some other activation function. But we are only talking about ReLUs right now. And then you take the output of the ReLU and you do 1 minus this output. And this gives you, I claim, the disjunction. So why is this true? So suppose, for example, that at least one of the inputs is 1. At least one of them is 1, and the others can be 0, but at least one of them has to be 1. In this case, right, when you do minus Q1, minus Q2, minus Q3, you will get at least minus 1. Right? It will be minus 1 or smaller. Right? It can be minus 1, minus 2, or minus 3. And once you have this, you add 1, you get you get either 0 or minus 1 or minus 2, and then the ReLU zeros everything out. So you get here a 0 if at least one of the inputs is 1. And then you have 1 minus 0, which gives you 1. So in other words, if at least one of the inputs is 1, you get back 1. But if all the inputs are 0, then you get here 1. Right? It's 1 minus 0 minus 0 minus 0 is 1. And then the ReLU gives you 1, and then you have 1 minus 1, which gives you a 0. So in other words, this computes exactly the disjunction. So if one of the inputs is 1, the output is 1. If all of them are 0, then this is 0. And then finally, once you have, so each of these is the result that you get from one of the clauses. Once you have these, remember, you need all of the clauses to be satisfied simultaneously. So this you do by simply summing up the outputs of each of the individual clauses, and then you get one final output y. And then as part of your output property, you just say that y needs to be equal to the number of clauses. And this is true if and only if all of your conjuncts are 1. Right? Because you have n clauses, only if all of them are 1 will this y be equal to n. If you put all of this together, it looks something like this. Right? So these are your inputs to the neural network, which are the variables that you have initially. You use them to compute your clauses. Right? So each of these is a clause. You negate the variables if you need to, and you use them to compute the clauses. These are the outputs of the clauses, and then you just sum up all of these outputs, and you get back one output for the neural network, which represents the number of clauses that you have satisfied, and this will be equal to n if and only if you have a satisfying assignment. So in other words, you can reduce the Boolean satisfiability problem into neural network verification. So here I made one simplifying assignment. I said that for every input, we allow it to be either 0 or 1, which is not consistent with the fact that I said that we allow linear conjunctions, that our constraints are only linear conjunctions. But this is a very simple limitation that you can get rid of. So I won't show you how, but if you're interested, you can find this online. So this completes the reduction, and hopefully the key point I think is that you can use ReLUs, for example, to compute disjunctions. And so you can use them to compute very complicated things. Any questions about the reduction? Remember, you can also write in the chat if you prefer. Okay. So you might say, okay, so this is very nice, but what about more interesting variants of the verification problem? So it turns out the problem remains NP-complete even if you allow P and Q to have arbitrary Boolean structure. This is perhaps not surprising because we just saw that you can use ReLUs to solve also disjunctions, to express disjunctions. And you can prove this by adding a few neurons to the neural network that will encode the Boolean structure of your formula. I won't go into this, but this is possible. So really what it is enough for us to focus on is just conjunctions, because all the other problems are reducible to this simple setting. You might say, okay, well, how about other activation functions, right? So we only talked about ReLUs. It turns out that, again, many problems can be reduced to the ReLU setting. Right, so for example, if you have max pooling, which computes just the maximal value among its inputs, you can express that also in terms of ReLUs. Right, so for example, remember, ReLU you can obviously express it using a max constraint because this is by definition. ReLU is just a max of x and 0, but it also goes the other way around. Right, if you want to compute a max, you can use it. You can compute it using a ReLU. Right, so it turns out that the max of x and y is just the ReLU of x minus y plus y. If x is greater than y, then this gives you back x minus y, and then the minus y and the plus y cancel out, and you get back x. But if y is greater than x, then this gives you 0, and then you are left with just y. All right, so again, the takeaway point is that it is enough in many occasions, in many cases, to focus only on ReLU constraints and conjunctions, because many other problems are reducible easily to this setting. Okay, so we talked about neural networks and we defined the verification problem and we showed that it is hard to solve. Right? It's NP-complete even for simple networks with simple properties. And we know that real networks can be quite large. So what can we do? Right? So how can we still solve this problem? So in the remainder of the slides, we will talk about the state of the art. So what people are doing today to solve this problem. And then I will focus more on one particular technique, this ReLUplex, which is SMT-based, an SMT-based technique. And I will also tell you a little bit about the evaluation later. So let's see what people have been up to, right? So how can you verify neural networks? So here there is a disclaimer that this is a very, very hot topic with literally hundreds of papers in the last couple of years. So obviously I won't enumerate and mention all of them. I will only mention a few samples that I hope will give you a sense of what people are doing. But of course, there are many papers and interesting techniques that I won't be able to cover today. So the main challenge that people are working on in the verification community of neural networks is scalability. All right, so because neural network verification is NP-complete, scalability is difficult. But we are not concerned by this because, as you know, this is usually the case in verification, right? For example, in SAT solving, you know that this is another NP-complete problem, and yet we have modern SAT solvers that can scale to very large instances. Right, so people are working on scalability, and this is a significant challenge, but we believe there will be a solution. And roughly dividing the techniques into two categories, people are trying two different things. So one approach is the sound and complete approach. Right, so sound and complete means we will be able to successfully solve any benchmark. And here the scalability is limited because of the NP-completeness nature of the problem. But you are guaranteed that you will be able to solve everything. The other kind of approach that people are trying is sound and incomplete. And here they're saying, well, look, we will trade away completeness, right? We will perhaps not be able to answer all questions. We might say, I don't know, I can't answer, but you can get better scalability. So these are roughly the two kinds of categories that people are looking into. There are some orthogonal directions, for example, abstraction, which I think is one of the more promising directions right now, but I won't talk about that today. And there are many other related approaches like testing and training techniques that are meant to give you neural networks that are verified, but I really won't have time to go into all of those today. And this is usually the point that people ask, well, how big is the network how big a network can you verify, right? Where is the state of the art today? So this is a very, very difficult and tricky question. And there are several reasons. One reason is that the property that you're trying to verify makes a huge, huge difference. And so you can have a very small network with a very complex property that will be difficult to verify, or you can have a very large network and a very simple property that will be easy to verify. You also need to compare complete and incomplete techniques, right? So you may be able to scale to large networks and properties with incomplete techniques, but they may also not be able to answer. Differences in implementations, of course, and people are using different benchmarks, right? So this is the disclaimer. It's very difficult to answer this question. But still, if I had to give a question, an answer, then I would say that the complete techniques today, well, maybe this already should be thousands to tens of thousands of neurons. Right, so this is roughly where the state of the art is. And the incomplete techniques typically do tens of thousands of neurons and maybe a little more than that, but not much more. So this is where the state of the art is in general today. Again, with the exception that a very simple property might allow you to scale more, and a very difficult property, a very complex property might make you scale even less. But in general, this is where we are at today. Any questions or comments? No. Okay. So now let's see what people have been up to. So I think one of the first interesting papers in this field is a tool called Never by Pulina and Tacchella from 2010. And they were among the first folks to try and verify neural networks. And they focused actually not on ReLUs, but on neural networks with sigmoid activation functions. And the main idea was to over-approximate the sigmoids and then apply interval arithmetic. And they actually used the SAT solver, an SMT solver to solve this, a solver called HiSAT. So what are these over-approximations that they use? So this is a very common theme that folks are using in verification. And the core idea is to take a system S that is complex and replace it with a simpler system S bar that is easier to verify. And the idea is that you make sure that all of the behaviors of S survive and are also included in S bar. But you might also introduce additional spurious behaviors, right? So things that only exist in S bar, but not in S. And because S bar is much simpler, you verify it instead of verifying S. And if you are able to show that S bar is correct, then so is S, because all of the behaviors of S are also included in S bar. So graphically, it looks something like this, right? So suppose you have a system S that is complex, maybe because you don't know how to work with cycles, and you over-approximate it using a system S bar that is a square. And maybe squares are, for some reason, much more easy to verify. And all of the behaviors of S are also included in S bar. And so if S bar is correct, then so is S, because all of the behaviors of S also exist in S bar. But if S bar is incorrect, then you need to ask yourself, is the counterexample that I got really a counterexample for S? Right? Is this something that shows me that S is incorrect? And then I can stop. Or if I happen to get an example here that is outside of S, then this is what we call a spurious counterexample. And then this doesn't tell me anything about S. Either S is correct or it is not. I don't know yet. And what people usually do in this case is they refine S bar. Right? They change the over-approximation to rule out, to not include this green dot. So this is over-approximation at a very high level. And this is a very famous technique in verification. So how did Pulina and Tacchella apply this technique to the verification of neural networks? Well, they said, okay, we have this sigmoid function. So let's approximate it using these rectangles. Right? So each rectangle contains a piece of the function, but it also includes other points, right? The other points in the rectangle, which do not fall exactly on the sigmoid itself. And then they only said for every x that is in one of these rectangles, we only know that the output is in the rectangle. Right? So we don't really take into account the exact sigmoid, but rather only these rectangles. And when a spurious example is found, we just make the x segments smaller. Right? So we switch to using more additional rectangles. And of course, the more rectangles that you have, the closer the approximation becomes, and the less likely you are to get a counterexample. So this was the first attempt that Pulina and Tacchella suggested, but this was of very, very limited scalability, and they could only scale to networks that had about 10 neurons, which is really too small to be of interest. So this was the first attempt that we have. Any questions or comments from anyone? No. Okay. So then there was a break, right? So between 2010 and 2016, I don't think there were any papers, or at least none that I read. And then in 2016, there was an interesting paper by Osbert Bastani and his colleagues, which didn't really study verification exactly, but they have some ideas that were very useful. So this is a technique for evaluating a network's adversarial robustness, so measuring how robust a neural network is to adversarial perturbations. And the idea is to do a reduction from something that is similar to the verification problem to linear programming. And this turned out to be a very interesting idea. So just to remind you what linear programming is, so a linear program is a set of linear constraints. Right? So you have a set of variables x, and you have a set of constraints. Right? So you know that some matrix A times x gives you some vector B, and you know that your x's, each of your x variables has an upper bound and a lower bound. And the question is to find an assignment that satisfies these constraints for which this objective function is minimal. So this is a linear program, and linear programming is a very well-established field in computer science. Is useful for many problems. And intuitively, what Bastani and colleagues suggested was to well, this is what I said just now. Okay, so I should have said also that this problem is known to be solvable in polynomial time. Okay, and there are very powerful tools that will solve it for you. So what did Bastani and his colleagues suggest? Well, they said, okay, let's look at each of these ReLU constraints that we have. And as we saw previously, these ReLU constraints are what's causing the problem to be complex, as we saw, difficult, as we saw in the reduction before. And we said, okay, let's look at each of these ReLUs. And we know that each ReLU has two phases. Right? Either it's active, meaning that x is non-negative and the output is the identity function. So notice that you can write this as a conjunction of linear constraints. Or it's inactive, meaning that x is not positive and y is 0. So again, linear constraints. Right? So in each phase, the ReLU really becomes a linear constraint. And what they suggested was that if we know that a ReLU is in a specific phase, then we should discard it. We can remove the ReLU constraint, and instead we can introduce this linear constraint. Right? So if the ReLU is in the active phase, we introduce this. If the ReLU is inactive, we introduce that. But the key point is that you can take a ReLU which is not a linear constraint, and consequently you cannot encode it in a linear program, and you replace it with linear constraints if you know that it is in one of its two phases. So what exactly did Bastani et al. Suggest? They said, well, let's look at a particular input point x0. Maybe this is the panda that we are checking, right? And we're looking for adversarial examples around this panda. And we can encode the entire neural network into a linear programming solver, right? We can encode all the weighted sums as linear equations. And we will evaluate the network for this particular x0. And for every ReLU in the neural network, we will see if this particular ReLU turns out to be active for x0, we will replace it with the active constraint, which is linear. But if the ReLU turns out to be inactive, we will replace it with the inactive constraint, which is also linear. And once you do this, you have effectively translated all of your ReLUs into either these linear constraints or these linear constraints, but in any way, the ReLU has been translated into a linear constraint. And then everything is encoded as a set of linear constraints, and an LP solver will very efficiently solve this problem and look for adversarial inputs for you. And they evaluated this approach on some image recognition networks, and they showed that this was very, very efficient. Okay, they could solve these problems very, very quickly. But of course, this is incomplete. All right, so when you take a ReLU and you're only looking for adversarial examples at either its active phase or the inactive phase, you never know whether there isn't another example that you simply didn't check because you guessed incorrectly. All right, so if you discover an adversarial example, then it is truly an adversarial example. But if you are unable to detect such an example, then you don't know whether there really isn't one or you simply didn't find it. This is an important point. So if anybody has any questions, this is a good time. Okay. So what you can easily do, right, with this idea is do a complete reduction from the verification problem into linear programming using a very similar technique to what Bastani and colleagues suggested. And this is what we call case splitting, right? Which I'm sure is a term you've encountered in this winter school already. So the idea is that you take each of your ReLUs, you guess whether it is active or inactive. You get a linear program, right? Once you guess active or inactive, the ReLU translates into a linear constraint that you can encode as a linear program and then solve. If you're able to find a satisfying assignment, then you stop and you say SAT, right? You have your counterexample, you have your satisfying assignment. And if not, you go back and you try another guess. You say, okay, maybe I guessed incorrectly for one of my ReLUs, and I will simply flip it. I will change to the other phase, and I will try again. And only when all of your guesses are exhausted do you stop and you say unsat. Okay, so this is very, very similar to the naive algorithm for Boolean satisfiability. And you just check all of the assignments for your Boolean variables. You assign something, you check if the formula is satisfied. If so, you stop. If not, you check another guess. And of course, in the worst case, you will have to traverse a very, very large search tree. Right? You will need to guess all of the combinations, which of course is prohibitively large. So again, this I'm sure you've seen this before, when probably in Armin's talk, right? So if you, for example, have two ReLUs, y1 and y2, each of them is a ReLU of x1 and x2 respectively, then in the root of the search tree, you don't know anything about either one of these ReLUs, then you can guess, right? So maybe you guess that the first ReLU is active, then you say that x1 is non-negative and y1 is equal to x1. You get to this node. Now you guess for the second ReLU, and then you get to a leaf of your search tree. And in this leaf, you have a completely linear program which you can solve. If you get unsat, you need to go to the next leaf and the next leaf until you either find a leaf that is sat, or until you have exhausted all of your leaves and all of them are unsat. And the key point is that each ReLU constraint in your neural network corresponds to a layer in your search tree. So the number of layers corresponds to the number of neurons, and the number of leaves will be exponential in the number of neurons that you have in your neural network. So this is a useful way to think about this, right, as a search tree. So you can take this case splitting approach and apply it, and you will get a sound and complete verification approach. This is what we do in ReLUplex, of course, with some other enhancements that we will talk about later. And there's really, as we know, this approach is very, very sensitive to heuristics, much like SAT solvers. So you really want to have good heuristics, and you also are always looking for tricks for curtailing the search space, right? For identifying branches of your search tree that you don't need or want to check. And there are many, many variations and enhancements that folks have suggested for this approach. So I listed just 5 of them here, but there are many, many more. So these are the sound and complete. This is the sound and complete family of approaches, and all of them internally rely in one way or another on this case splitting. Right? You guess one way or the other, usually for the ReLUs, and you try to solve. And in the worst case, you need to do an exponential number of steps. Any questions on the sound and complete approaches?
Are you going to get into details about how the conflict clauses here work, or how do you do conflict
just a little bit.
analysis?
I will talk a little bit about this.
Okay, then I'll wait for that. Yeah.
Okay.
Hi. So you'll generate the formula on the fly. So you cannot get a formula until you reach a leaf node.
So so everything is given to you in advance, right? So you are given all of your constraints at the beginning. This is the input to the verification problem. You get your neural network, and the neural network has a set of ReLU constraints, and it has a set of linear constraints. And you get all of these constraints immediately from the beginning. But the problem is that you don't know how to solve the problem as it is, right? You don't know how to solve it always in the root of the tree. And what you do is, in this case splitting approach, you guess for each of the ReLUs whether it is active or inactive. And once you have guessed over all of your ReLUs, then you get your final, when you get to a leaf of the search tree, then you get to a problem that only contains linear constraints, and you can solve it. Right? So all of the constraints are given in advance, but you need to do some guessing, right? You need to do some case splitting.
Okay, thanks.
Sure. Anyone else? Okay. So now let's talk a little bit about the incomplete approaches that folks have been trying. So one famous one is called DLV. This is an approach by Zhuawi, Huang, and colleagues. And this implies an idea of discretization of the input space. Right? So what they suggested was to do these manipulations. They said, okay, suppose we are thinking about adversarial robustness, then we're not talking about a random perturbation that might happen to the input, but rather we are interested in certain things that we know are likely. So maybe a scratch on the lens, or maybe glare from the sun. These are not random changes, but these are what they call manipulations. And this approach, when you only talk about manipulations, they proposed an exhaustive search technique that is sound and incomplete. Right, so the idea is that you start at some point in the input space. Maybe this is the panda. And the rectangle here is the amount of noise that you are allowed to add. And because you have a finite number of manipulations of these changes that can happen, you just try all of them. And so you say, maybe I have a scratch like this. Maybe I have glare from the sun like this. Right? And then you just explore all of the changes that can happen in your rectangle, and you can find counterexamples like this. Okay, so this is sound because if you find a counterexample, it is truly a counterexample. It is an adversarial example. But if you're unable to find anything, then you don't know whether there really isn't an adversarial example, or simply you looked at the wrong, right, in quotes, manipulation. Maybe another manipulation can happen for which there will be a counterexample. So this is a tool called DLV. It's also fairly well known. Another very interesting line of work is something called abstract interpretation for neural networks. And here the authors take this geometric approach, and they said the following. Let's look at the input property that we have, the precondition. Let's over-approximate it using some geometric shape, like a polyhedron, sorry, and then you propagate this polyhedron layer by layer. So for example, if you have, maybe this is your input layer, and you are interested in this region here, in dark gray. This is the true input region that you are after. And maybe this input region has a very complex shape that you are not able to work with. So what you do is you over-approximate it, maybe by a square. And so the square over-approximates the region that you really care about. And once you have this convenient shape, the square, then you can show what happens to the square when you pass it through a layer of the neural network. So you pass it through the first layer, and you see that the square here is stretched into a rectangle. And you know that it will always contain all of the input points, where the input points are mapped to in this layer, but you get shapes that are very easy to work with. So this is very similar to the over-approximation idea that we discussed before. And in AI Square, this abstract interpretation for artificial intelligence, they showed how to do this for a neural network in a very nice and efficient way. But this is, again, a sound and incomplete approach. Right? So you know that if you find a counterexample, it will truly be a counterexample. But if not, then maybe a counterexample simply doesn't exist. I will just briefly enumerate a few of the other techniques because there's really so many of them. So you can treat a neural network like a continuous function and analyze it. This is something called Lipschitz continuity that you can look into. Lots of papers on this. Folks have now started focusing also on binarized neural networks where the weights are binary. And typically there is a reduction to SAT solving involved. So lots of interesting work there also. People have used quadratic solvers and other techniques, really many things. And really, I think I will, you can have a look at the references afterwards if you want. They're all included in the slides, but I won't go into this right now. So going back to the roadmap. So we know that neural network verification is hard. Right? It's NP-complete even for simple networks and simple properties. When we've just seen that it is reducible to an exponentially long sequence of easy problems. Right? If you do this case-splitting approach, then you can get an exponentially long sequence of linear programs that you can solve very quickly, each of them, but because their number is so large, this will take a long time. So this is the sound and complete approach, and we have seen that people have been trying to trade away completeness for better scalability, and we mentioned some of these techniques very quickly just now. And in addition, you can also combine each of these techniques with abstraction, which I won't talk about today. And next, we will focus on one sound and complete technique called ReLUplex, which really emphasizes the SMT angle of neural network verification. So any questions on what we've seen so far? No. Okay. So now let's talk about ReLUplex. So first I should mention that this is based on a paper that I co-authored with these folks here. So this is Clark Barrett, Dave Deal, Kyle Julian, and Michael Kockendorfer, all of them from Stanford University. And this is a paper that appeared in CAV 2017. And here we propose this ReLUplex approach, which is a sound and complete verification procedure. And we successfully applied it to the ACAS Xu case study. So this was an interesting, an interesting result because we were really able to take a set of neural networks that were safety critical and really in use by a real agency, and we were able to verify them. And I will tell you some more about the evaluation later on. And I should also say that this is a very active research project even today. So the successor to ReLUplex is called Marabou. It's available on GitHub. It's free. It's open source and under a very permissive license. So if you need to verify a neural network, I encourage you to try and play with this tool. So what is ReLUplex? So it's really an SMT solver for quantifier-free linear real arithmetic plus ReLUs. Right? So if you think about a neural network, you have the linear constraints, right, which are linear real arithmetic, and you have these ReLUs, which are not immediately supported. And what ReLUplex does is let you solve linear real arithmetic with the ReLUs incorporated inside without doing the case splitting. So it's based on simplex. Simplex is an algorithm for solving linear programs. This is also where the name comes from, right? It's ReLUplex. It's a simplex with ReLUs, and hence ReLUplex. And although it was initially designed for ReLUs, you can also use it for other activation functions. As we saw, for example, max constraints can be immediately reduced to ReLUs, and you can do this really for any piecewise linear activation function. And the key idea that we took from the SMT literature, which also, of course, exists in SAT solving, is this lazy approach. All right, so you don't take the problem, the piecewise linear constraints, and guess. You don't eagerly guess the phase of each ReLU, but instead what you do is you handle the ReLUs very, very lazily. And this we will see in an example soon. And you really want to defer the splitting for as long as possible, right? So you don't guess unless you really have to. And it turns out that in many cases, you don't have to split at all. But before I can show you ReLUplex, I need to show you an introduction to simplex. Right? So we need to know the basics of simplex before we can build on them and extend it into ReLUplex. So simplex is a very ancient algorithm in computer science. It was developed after the Second World War by George Dantzig here. And it's just an algorithm for solving linear programs. Okay, so no ReLUs, just linear equations, variable bounds, and also an optimization goal given as an objective function. And it turns out that this algorithm is very, very efficient, and it's actually still in use today. Right? So it's although it's quite old, it's still considered a very good algorithm. And in simplex, what you typically have is two phases. So in the first phase, you are looking for a feasible solution. Right? So remember, we had constraints on the variables. Right? So first, you find one assignment that satisfies the constraints, and you don't care about the objective function. And then in the second step, you try to optimize this function, this assignment with respect to the objective function. So simplex typically has two steps. So this is step one, this is step two. But we will only focus on the first step, right? Because when you want to solve a satisfiability problem, you're only interested in finding a feasible solution or determining that no such solution exists. So we won't talk about optimization today. There is an interesting application, of course, also to optimization, and there have already been papers on that, but I won't talk about that in today's tutorial. So simplex for phase one is an iterative algorithm, and the idea is that at every iteration, it maintains a variable assignment. And this variable assignment always satisfies the equations that are given as part of the input, but it may temporarily violate variable bounds. We will see an example soon, so don't worry. And in every iteration, what simplex does is an attempt to reduce the overall infeasibility. It tries to satisfy more constraints that were previously broken. So simplex typically divides the set of variables that you have into basic and non-basic variables. And the non-basic variables you can consider as free, right? You can assign them to any value that you want. and the basic variables are bounded. Right? So once you assign values to the non-basic variables, the basic variables get a value automatically. So the assignment for the non-basics determines the assignment for the basic variables. And this is how we make sure that the equations are always maintained. And in every iteration, we can perform one of two steps. We can either do an update step, in which we change the assignment of a non-basic variable and any affected basic variables. Or we can do a pivot step in which we switch a basic and a non-basic variable in order to manipulate the equations. I imagine this is not very clear, so let's jump to an example. So this will be our toy neural network for this part of the slides. So we have one input node, one output node, and two hidden nodes here. And for this part of the presentation, we're going to assume that there are no activation functions. Okay, so only weighted sum. Remember that simplex is a technique for solving linear programs. So it doesn't know how to do things like ReLUs, which are not linear. So for now, we assume that everything is linear. Okay, so just the weighted sums. And this is the property that we're trying to check. We're asking, does there exist a point x1 that is between 0 and 1, such that x4, the output, will be between 1/2 and 1. Right? So we are always negating the property. So we want to prove that x4 is never in this range, and we will do this by asking, is it possible that x4 is in this range? Now, you might notice that no matter what you assign to x1, because there are no activation functions, x2 will be equal to x1, x3 will be minus x1, and then x4 will be x1 minus x1, so it will be 0. Okay, so we expect to get ansat for this, because it doesn't matter what you assign to x1, x4 will always be 0, and so it will never be between 1/2 and 1. Any questions on the example before we proceed to see how simplex solves it? No. Okay. So now let's see how we can solve this problem using simplex. Okay, so first we translate this into a linear program. So how do you do this? So first you take the weighted sums, and for each of them you introduce an equation. So each weighted sum gives rise to one equation. For example, x2 equals x1 gives you this equation. x2 minus x1 is 0. x4 is x2 plus x3 gives you this equation. And so really every weighted sum in the neural network is translated into an equation. Then in a linear program, the other thing that you have is also bounds. Right, so we specify variable bounds. So we say that x1, the input variable, is between 0 and 1. This is part of our input problem. Right? This is the constraint that we get. x4 is between 1/2 and 1. So again, bounds on one of the variables, again, part of the property that we are checking. And the hidden variables, x2 and x3, we don't care. We say they are unbounded. Right? They can take on whatever values they want. So this is an encoding of this problem as a linear program. Now, typically, simplex doesn't like these constants floating around. So what we do is we replace them with auxiliary variables. So we introduce 3 fresh variables, x5, x6, and x7. And we require that they be precisely 0. And we replace the zeros here with these fresh variables. So this is a purely technical step. It doesn't change anything. And the key point that I hope you are convinced of is that if we are able to find an assignment to the variables that satisfies the equations and satisfies the bounds, then we have found a counterexample for the neural network, and for the property that we are trying to verify. And if no assignment exists, then we know that the problem is unsat. So how do we solve this? So we said that simplex is an iterative algorithm, right? So now we're looking just at the linear program. We're looking at the equations and the bounds, and we don't care about the neural network right now. So x5, so these equations, right? So x5, x6, and x7, these are the equations from before. So we keep the equations. And this is the state of simplex, right? So for each variable, we have here all the variables in our system of equations. For each of them, we have a value. Currently, all of them are 0 initially. And for each variable, we can have a lower bound and an upper bound. So for example, x1 is between 0 and 1. Where a bound is not written, this means that the variable is unbounded. So remember, we have this invariant that says that the equations will always hold. The equations must always be satisfied. So initially, when we assign all the variables to 0, we trivially satisfy all of the equations. And now we will use simplex to determine whether there is a satisfying assignment in which the variables will also satisfy their lower and upper bounds. So we start in the first iteration of simplex. And simplex looks at the current assignment, and it says, well, here is a problem. x4 should be at least 1/2, but it's currently set to 0. So x4 is too small. How can we change this? we do an update step. So an update step simply changes the assignment of one of the variables. So we take x4 and we increase its value by 1/2 so that it meets its lower bound. Right? It's too small, so we increase it. So the assignment for x4 changes from 0 to 1/2. But because x7 depends on x4 using this equation, because we changed x4 from 0 to 1/2, x7 was also increased from 0 to 1/2. So this is how we always maintain the equations. When we touch a variable, we make sure to update any variables that depend on it. So at the end of this first iteration, x4 has been fixed, right? It's now no longer violating its bound, which is good. So we finished the first iteration. But now in the second iteration, we have a problem with x7. x7 should be at most a 0, but it's currently 1/2, right? So it's too big. So now we need to fix x7. And x7 is different from x4. And this is the distinction between basic and non-basic variables. Everything that is on the left-hand side of an equation is a basic variable. And everything that's on the right-hand side is a non-basic. So x4 was non-basic, so we could just play with its value and then update the value of x7 accordingly. But because x7 is left-hand side, because it's basic, we can't just change its value. We first need to make it non-basic. And how do we make it non-basic? Using a pivot step. So we just take this equation, and so this is the original, this is the original equation. And we do a simple arithmetic operation. We take x2 and we switch it with x7. So we get this, right? So x2 is now basic and x7 is now non-basic. It's exactly the same equation. It's a trivial arithmetic manipulation, but this will make x7 non-basic. Now there is a problem that we don't want x2 to be both basic and non-basic. So if we made it left-hand side, then we will also eliminate it from every other equation in which it appears. So we substitute to remove x7 from this equation also. And after this pivot step, what we get is a new situation in which now x7 is non-basic. It's right-hand side, and we can play with it. So because we want x7 to be at most 1, 0, now at most a 0, then now we can do the update step and reduce its value from 1/2 to 0. So the value for x7 reduces, right? So it becomes a 0. And now because x5 depends on x7 and because x2 depends on x7 and we reduced x7, then these two guys need to increase, right? Because of the negative sign. So the assignment for x2 and x5 increased to 1/2. And now when the second iteration is done, right, x7 is good. x7 is not too great. It's precisely where it needs to be. But of course, now we have a new problem. Right now, x5 is too small. It's too great, sorry. It should be at most a 0, but it's 1/2. So simplex does yet another iteration. All right, so x5 that we want to decrease is a basic variable, so we need to do a pivot. So we do the same thing as before. We update the equations, and now x5 is here. Right, so it's a right-hand side variable. It's non-basic. And now we can do an update step that decreases x5, but increases the variables that x5 influences, that is x1 and x6. And then in the final iteration, we look at x6 and we say, well, x6 is now too great. We need to decrease it. And now simplex says failure. And where did this failure notice come from? Well, x6, remember, it needs to decrease. But if you look at its equation, you will see the following. So x6 depends on x4, right? And x4 has a positive coefficient, right? A +1. So in order to make x6 smaller, x4 needs to decrease also. But x4 is currently pressed against its lower bound. So it doesn't leave us any slack, right? We cannot decrease x4 anymore. Or alternatively, in order to make x6 smaller, you could increase x7 or x5. But x7 and x5, each of them is already pressed against its upper bound. So they also don't leave us any slack. So in other words, we cannot decrease x6 at all. We cannot decrease x4 and we cannot increase x7 or x5. So this means that we have reached a minimum for x6. x6 can never be less than 1/2. And this, of course, contradicts the fact that it needs to be at most 0. So this is how simplex says failure. It says unsat. And this makes sense because this is what we were expecting. Right? We said that x4 could never be between 1/2 and 1. So of course, I didn't define simplex fully. This is just an example, but I hope it conveys the intuition behind this algorithm. Does anybody have any questions on simplex?
A quick question. Can a variable be basic for two different constraints? Because when you substituted, why not just rearrange so that x2 is also basic for the first?
So you don't allow that. So each variable can be basic for one equation only. This is how simplex is defined.
Okay. Thanks.
Okay. So I think one more slide and then we can take a break. So just the properties of simplex. So it is a very famous result that the simplex algorithm is sound and complete with a little star. So what does it mean? So soundness means that if simplex says SAT, then the assignment that it finds is correct. And if it says unsat, then there is no assignment, right? So you can really trust this algorithm. And completeness, as it turns out, depends on the variable selection strategy. So in some cases, you have multiple options, right? When we do a pivot, for example, then you can pick which variable you switch the basic variable with. And sometimes you have multiple options. Additionally, sometimes you have multiple violated constraints, and you need to think which one you fix first. So this is called the selection strategy. And simplex is really influenced by the selection strategy that you use. And we know that there are certain selection strategies that guarantee termination. And so there are variants of simplex that are guaranteed to be complete, to terminate. But as it turns out that these strategies that guarantee termination turn out to be quite slow. So people actually use other strategies that are much faster in practice, but do not guarantee termination. So it's complete with a little star. Okay, so there is a version of it that is complete, but people usually use faster variants that are not guaranteed to terminate. And finally, we know that the problem of linear programming is in P, right? So it's solvable in polynomial time. But simplex, actually, the algorithm, we are not sure yet, even after so many years, whether it's in P or not. So again, this depends on the variable selection strategy. And right now, for every known variable selection strategy, there is an example on which an exponential number of steps is required. It is an open problem whether there exists a variable selection strategy for which only a polynomial number of steps is required. But still, although simplex is probably exponential, in practice it is very efficient. And that is why it is such a popular algorithm. Okay, so I think we will stop here for 15 minutes. And then we can talk about ReLUplex. So see you back then.
Thank you. So I guess we can move to Discord, or maybe everybody takes some 15-minute break.